Alright, so in this last video, what I'm going to do is talk about electric potential in a couple of different scenarios and how it relates to electric fields. So if we had a parallel plate, so we've actually talked about parallel plates already, and we know a little bit about them. So a parallel plate would have a positively charged plate and a negatively charged plate. And when they are next to each other, a uniform electric field arises. So you have an electric field that points away from the positive and towards the negative. Now, if I were to place, say, an electron into this electric field, it would have a force acted upon it, and it would be attracted to the positive plate in this direction. And I'll kind of draw it with a dot so we can see it. And so I know that if a force is acting upon it, then it's going to want to move from here to here, and its potential will change. So there has to be a potential difference between this plate and this plate. So just to give you an idea of the practicality of a parallel plate, like where do we actually use it? A parallel plate is typically attached to some wires that then is attached to a source. So in this case, it's a battery. And we'll say that the battery is a 9-volt battery. So when you hook the plate up to a 9-volt battery, what happens is the electrons start getting attracted to the positive end of the battery, and they start being repelled by the negative end of the battery. So we end up pulling electrons off of this guy and shoving electrons onto this guy. And so we end up developing this parallel plate scenario where you have a positive side and a negative side. And this happens until the potential in the battery is the same as the potential difference of the plates. So the potential difference of the plates would also, in this scenario, be 9 volts between all the way from here to here. Now, where this would be used, the most common example, or maybe something that make most sense to you, is you want to store up electrons, or you just want to store up energy, so that we could release a whole lot of energy very quickly. So an example would be a flash of a camera. So sometimes when you turn on a camera, you can hear the flash go whoop, or make this sort of noise. That's charging up the capacitor, which then it could be released and all come out in a very quick burst of light. All right, so we have a potential difference, we have an electric field, and we know that this object, this electron, can move in between these two plates and change its potential, change its energy, and change its velocity. So there is another equation that we can use with the parallel plates. It also can be used for a non-uniform field too, if you know potential difference. But the equation relates electric field volts and the distance between the potential difference. So let's say this plate is designed to be 0.02 meters away from each other, right? Again, we could also do this in the scenario where you had positive and then you had a negative, and you said, okay, this electron moved from here to here, and as it did that, it went 0.02 meters, and the difference in potential from here to here was 9 volts. It would be the same exact scenario. But the equation is that the electric field is equivalent to volts over distance, right? So I could figure out the electric field in between these parallel plates, and I would say that electric field is 9 volts over 0.02 meters. And if I plug that into my calculator, I actually get 450. Now, we learned that the unit for electric field is newtons per coulomb, but we can also use another unit for electric field. In this case, you might see it as volts over meters. So that would be the same thing as saying 450 volts over meters. Okay? Those are both equivalent to the magnitude of the electric field at this, undergoing this change and in between these two parallel plates. Now there's one other sort of common scenario that, or item that we've been talking about, and that is a conducting sphere. So a conducting sphere is a piece of metal that allows electrons to distribute over its surface. And essentially, once we start to flood this sphere with electrons or add electrons to it, the electrons are going to repel one another, right? So they are going to set up what is called an equipotential. And that means that they are going to just evenly distribute themselves across the surface of this sphere, so they are all exactly the same distance apart from one another, right? They do not want to be coming in contact with one another. So they're going to repel each other until they're all spread out over the surface of the plate and they have equal potential. So essentially what happens with this conducting sphere is we say that it's an equipotential surface, but we also say that the net electric field, because they're all equally distant apart, is 0 within the plate or within the sphere and on the surface of the sphere. Now, however, they do generate an electric field that radiates out in the area around them. So we would still have an electric field out here, but within the plate and on the plate, you would have no electric field. Now, if we just look back quickly at this picture again right here, and you did this in the lab, the charges and fields lab, but one thing to notice here is that we can have equipotentials within a parallel plate too. And equipotentials are just where a line would cross your electric field lines perpendicular to the electric field lines. So if I moved up or down here, I would be experiencing the same potential because I'm not moving closer to or further away from any of the charged plates. So we can have equipotentials in this scenario as well. All right, and so that wraps up static electricity. In the next unit, we'll start to talk about current.